Mm. All right, everyone. Thank you all for signing in for our new series of Galaxy SIG talks, science interest group for the NASA group. So I'm absolutely delighted to have Mia Bovill today for about galactic paleontology. Mia got her PhD in 2011 from the University of Maryland, and then she was a Fondesit fellow at in Chile, and then SDSCI, and she was faculty for a while at Texas Christian University, and now she's back as a researcher in University of Maryland. So I'm very keen to hear from her. All right, Mia, take it away.
Okay, I'm going to be talking to you a bit about galactic paleontology and the era of Habitable Worlds Observatory. And I should have put a little caret in there that said I'm also going to mention this other telescope NASA's going to launch called Roman, because when it comes to near field cosmology, Roman is going to revolutionize things. And so I think that to talk about this without talking about Roman would do a disservice to Roman and to habitable worlds. I wanted to particularly highlight two collaborators, Sachi Wiyosaria, who was my doctoral student at TCU. She's now a postdoc at Carnegie Observatory and is phenomenal and spectacular. And also Anshuraz Sadai, who is an undergraduate at Kabul University, who worked on some of this with me and will be looking to apply for graduate schools or post-bacs soon. So please keep an eye out for him.
Can you play the slides, or
Are we good?
I'm just seeing the
Now can you see it?
if you hit play.
I hit play.
Oh, I think it's
We don't
on.
see full screen.
We do, yes.
Wait a minute.
I think we might be sharing the wrong screen.
Okay, let me just a second. Give me a minute. My laptop isn't letting me. You know what? Worst case scenario, I can just not press play. Yes? Right. Okay, share. It works. Okay, can you see it
No.
when
Ah,
it's in this? When it's in this format, can you see it?
I can now see yeah, and the slides in the
But
sidebar.
when I hit
There it
play,
is. There it is.
can you now see it advance?
Yes.
Okay, perfect. Okay. So, and for anybody who is curious, this is the pictures I took of the eclipse in Mejia, Texas, because all astronomers for at least the next 2 years must show off their eclipse pictures. It's a contractual obligation. So this is just, I think we've all seen this graphic enough times that particularly for this group, I don't need to sort of explain it. But this is, of course, the timeline of the universe, not to linear timescale. So we have present day over on the right, and then reionization and epoch of recombination of the dark ages over to the left. And just as a reminder that the purposes of near field cosmology is to link what's going on at the present day, where we have all of these incredible observations and will have all of these incredible observations, but to what was going on during kind of this first billion years of the universe's history. And just as a quick reminder, that structure formation in lambda CDM is inherently hierarchical. And why this is important when we start talking about galactic paleontology and dwarf galaxies is because as smaller structures merge into larger and larger structures, the dwarf galaxies are sort of the detritus of those mergers. These are the smaller things that are merging into the larger halos. And what I'm hoping to convince you of over the course of this talk is that in addition to potentially giving us information about just the mass of the halo, the details of the populations of the dwarf galaxies actually tell us an incredible amount about the merger histories of the halo. And as we start getting observations with habitable worlds and with Roman, we're actually going to be able to really put some observational constraints on what the merger histories of the halos in the local universe look like. And this is a theory talk, so I am also contractually obligated to show at least one movie. And so at the end, you end up with the voids, with the galaxies running along the edges of the filaments. Around all of these big galaxies would be little swarms of dwarves. So near-field cosmology is basically using the smallest galaxies in the local universe and pushing them back to look at the first billion years after the Big Bang. And the reason that I've always called this galactic paleontology is that you're using basically these little tiny dead galaxies today to study the first billion years the exact same way that paleontologists study the Jurassic period. And Benny, there is something in the chat. I can't see the chat. Can everyone hear?
Yes,
I was just asking if we were recording the talk. Sorry.
We are.
I didn't mean to cause interruption. Okay, thank
All
you.
right, don't worry about it. Sorry. And also this is a really, really good excuse to use dinosaur pictures in an astronomy talk. So when we talk about near-field cosmology, we can actually now talk about the local volume. And this is a very rough image of the local volume centered on the local group, which is centered on the Milky Way and the local group made up of the Milky Way and M31. There are about 5 or 6 additional groups in the local volume that range in everything from Centaurus A, which is NGC 5128, that is potentially as high as 10 to the 13 solar masses and an elliptical, to something like the Sculptor group, which may not even be fully virialized. So there is a significant amount of diversity just within sort of 5 megaparsecs of the Milky Way. And this is well within the range of detailed observations for both habitable worlds and also for Roman. And just as a reminder that there is another telescope that NASA is launching, I do have a wooden desk in 2 years. This is the Roman Space Telescope. As a reminder, it will have the resolution of Hubble over 100 times the area. And when it comes to near-field cosmology, as we wait for habitable worlds to launch, this is going to be a critical sort of first step into really pushing near-field cosmology out well into the local volume and getting the first censuses of the dwarf satellites that's to date. One of the things I like saying is we talk about high redshift galaxies before and after JWST. I think for near field cosmology, it's going to be similar for Roman, that it's going to be before and after Roman, with then habitable worlds coming along and providing the optical and UV observations of many of these systems. So the question becomes, are we ready for this? Are we ready for these incredible revolutionizing near-field cosmology data sets that are coming along? And the answer is not yet, but I think we can be. So this is the status roughly of theoretical galaxy simulations as of about 9 months ago, is I think when I downloaded this. If your favorite recent simulation is not on here, I apologize. The critical thing to note is that the vertical axis is baryonic mass resolution. So basically, as you go further up, you have higher and higher resolution. The horizontal axis is the number of galaxies. So as you move to the right on the horizontal axis, you're going to places where you have higher and higher statistics. But one thing that's important to note is that 1, these are logarithmic scales. And 2, in general, there is always a trade-off in hydrodynamic simulations between having something with very high resolution but low statistics, or having significant statistics, so a lot of galaxies, so that you can look at variations in merger histories and environment, but you're not going to necessarily have the high resolution. And what I mean by high resolution here is the ability to resolve the ultra-faint dwarfs. So being able to push yourself down to dwarf galaxies that have 1,000 or 10,000 solar masses of stars, because that's where we're going to be with Roman and with habitable worlds observationally. And just for sort of comparison, TNG 50, which is highlighted here, can resolve roughly the SMC and the LMC mass systems. And the system in these high resolution, low statistics, this is fire, this is Justice League. So there are not actually that many of these. But so we need something that can do high statistics, but also provide this high resolution, get down to these really low masses. And the answer to this is actually semi-analytic models. Specifically, I'm going to be talking about the Semi-Analytic Model Galacticus throughout this talk. SAMs are able to provide high resolution, but also high statistics because of their computational efficiency. The trade-off is that the properties that you get in the semi-analytic models are global properties for the entire galaxy, rather than actually resolving things that are going on within the galaxy. So that's your sort of major sort of trade-off with the semi-analytic model. Also, we don't have really, really pretty movies, which is why I showed one at the beginning. So how does a SAM work? In fact, to some extent, this is sort of how all simulations, sort of hydrodynamic or any simulation with the baryons work. There's going to be some sort of, and I don't know if you can see my cursor, but there will be some sort of merger tree, that dark matter merger tree that is generated, and then one way or another, the baryons will be included in that. In hydrodynamic simulations, that is inherent. In a SAM, you generate that merger tree, and you can do it one of two ways. You can do it from a simulation that then you run through a Halo Finder, you generate the merger tree, and then you run the semi-analytic model on that merger tree. Or you can generate the merger tree statistically using extended Pressure theory. Either way, you end up with the merger tree with a given lambda CDM cosmology, and then you use the semi-analytic model to put the baryons on top of it. The semi-analytic model is then constrained to the observations, and I'm going to sort of walk you through that process, a little bit of sort of how exactly that's done. But you basically constrain to the observations, you pick very specific properties to constrain it to, and then you move on from there. And I just want to give credit, all of the stuff that looks really pretty in this talk, Sachi actually did. She's a phenomenal science illustrator, in addition to being absolutely a spectacular scientist. So why do this? An M-body simulation has an efficiency gain of about a factor of 100 over hydro. It can be as high as 1,000, depending on sort of the details of the codes. The extended pressures, where you're not running an M-body simulation, but you're statistically generating these trees, is about 1,000, factor of 1,000 improvement over the M-body. So compared to a high-resolution hydrodynamic simulation of a Milky Way analog, Galacticus is 100,000 to 1,000,000 times more efficient running with EPS trees. So in the time that a hydro simulation can run one tree, we can run thousands. And I would just like to say that all recognizable images throughout this talk are the property of Marvel, and we did check the Copyright Act. And what this shows here is the baryon cycle. So this is what Galacticus follows. There are prescriptions for the inflow of gas cooling, star formation, feedback, as well as tidal stripping and ram pressure stripping. And I am happy to discuss those more in detail if people have questions at the end. So what we need to do now is we need to pick a set of observations that we're going to compare and constrain Galacticus to. And the best thing to do for this is going to be the Milky Way dwarfs. This is the system that we have sort of the best census of and the most detailed information about sort of these systems. And what did we choose to do this? And what we chose was we looked at the luminosity function and the luminosity-metallicity relation. These are the two things that we constrained. This is from Sachi's first thesis paper, where we actually were using an M-body simulation of a Milky Way. The magenta throughout all of this is Galacticus. The observations in green are based off the updated McConaughey et al. 2012 tables, and we have also shown the Justice League and the fire simulations as well. And the reason for comparing the hydro simulations to Galacticus is because of the incompleteness in the observations below a magnitude of about -10. And we found that we can simultaneously match the luminosity function, and the luminosity metallicity relation. So we're able to basically reproduce the basic feedback of the Milky Way dwarfs. And what I want to draw your attention to is that we didn't tune this to do this, but we're actually going down to the brighter ultrafaint. So what you would think of as the ultrafaints found with the Sloan Digital Sky Survey. And this was a complete surprise, that we were actually able to have Galacticus push all the way down into the ultrafaint regime. And this was run on a laptop to give you a sense of the computational cost. So once you actually you've constrained things, you can then look at other properties. So we can look at the velocity dispersion, the mass to light ratio, and the half-light radii of the satellites. And what we found is we were able to match all of them. So these runs, I want to make a point that we have not, Galacticus is not constrained to reproduce the velocity dispersion of the Milky Way dwarfs, and it is not constrained to match the half-light radii. Or when I show you in a moment, the star formation histories. But it matches all of these, having constrained the luminosity function and the luminosity metallicity relation. Nuisha Havazi, who is currently a postdoc at UVA, as part of her thesis, added molecular hydrogen cooling into Galacticus. She also added something which statistically draws the orbits of satellites. So when the EPS tree says a satellite infalls, she added functionality that statistically draws that infalling orbit from a set of M-body simulations and then evolves the orbits forward. And this removed the major drawback of EPS trees for dwarf satellites, because we now have 6D phase space information for all of the dwarf galaxies in running with an EPS tree, which was before her work we didn't have. She's able to replicate, same thing, luminosity metallicity relation, the sizes and the velocity dispersions of the Milky Way dwarfs. And on the left here, you see the luminosity functions that she produced for LMC analogs, Milky Way analogs, and M31 analogs. And each of these was run with about 100 galaxies in that mass range. And something that I want to point out to you and to sort of note and put a bookmark on is the amount of scatter that she is seeing in these luminosity functions. So for halos that are purposely run at the same mass, you have luminosity functions that can vary by a factor of several.
Can I ask a quick question?
Yeah.
If you go back to the slide, yeah, here. You say there is a large scatter in the luminosity functions, depending on the halo that you consider. Does that scatter also shows up larger? I mean, does that scatter shows up in the other relationships or only in just, I have more or less galaxies depending on the halo? Or do they have different properties as well?
Spoiler alert, yes. I have some slides on that actually later in the talk, but it does actually. Okay. It shows there are overall trends, which I'll show you in a moment, but there are overall trends, but exactly where things fall does actually become very dependent on the halos, on the specific halo and the specific merger history. But phenomenal question, because that's exactly where I'm going. So the incredible sort of power of this is that you can pick any merger tree. So you can pick any merger tree of any mass, and the LMs and the local volume doesn't just have 10 to the 12 solar mass halos. We also have Centaurus A at 10 to the 13, and then you have clusters like Fornax and Virgo. And once Sachi and I had the properties we had Galacticus reproducing the properties of the Milky Way satellites, we decided to take it out for a spin with Centaurus A. And we used the exact same astrophysical prescriptions and parameters that reproduce the Milky Way. We did not tune this. And one of the reasons we didn't is because the data set for Centaurus A just isn't complete enough. We don't know the satellites of Centaurus A well enough to actually do the same sort of constrained tuning that we were able to do for the Milky Way. And in this case, the purple are the observations, the blue shows you the extended pressure trees, and the green is the results from the M-body trees for a Centaurus A analog of about 10 to the 13 solar masses. And we have included all satellites within about 700 kiloparsecs to account for the splashback radius of the Centaurus A halo. And you see this is, once again, the luminosity function, and we are, without any additional tuning, able to roughly replicate the luminosity-metallicity relation of the Centaurus A satellites. That suggests that the physics that is governing the dwarf satellites in these two systems, that again are an order of magnitude apart in mass, is actually the same, which was not unexpected, but a nice sanity check. We are also able to replicate the velocity dispersions and the half-light radii using both EPS and M-body for the Centaurus A satellites. And well, to the point where we actually have the data. Once again, these are not the complete sort of detailed surveys that we have for the Milky Way. But an important point to make here is that the EPS trees are doing just as good a job as the M-body simulation at replicating these properties. So this allows us to sort of say, you know what? We can use the EPS trees, especially with the orbital integration that Nuisha added. We can now just use the EPS trees to run this, which again gives us that factor of 1,000 speed up over the M-body simulations. So I want to sort of dig a little bit under the hood here about the actual metal enrichment. And the reason this is important is because, you know, we talk a lot about near-field cosmology in the sense of we're looking at what's going on at z=0, but we're actually able to, just with JWST, let alone as we move into sort of Roman inhabitable worlds, we're beginning to be able to detect dwarf galaxies out to significant cosmological distances and significantly further back in time. All of the work that I showed you up until now has assumed what's called an instant metal recycling method. This basically assumes that the stars form, all the supernovae go off at the same time, so the core collapse and the type 1As. They go off at the same time, and then you assume that the relative metal fractions of, for instance, oxygen to iron is solar. And that works incredibly well if you're mostly looking at more massive galaxies or more massive dwarfs at z=0. But if you're starting to look at low mass systems, that may be the fossils of the first galaxies. If you're talking about potentially looking at dwarf galaxies throughout significant fractions of cosmic time, you can no longer assume that the oxygen to iron yield is solar. So this is actually an assumption that we know is likely wrong. And one of the things that Anshura Sadai has been working on with me on is basically debugging and looking at non-instant metal recycling. So this treats the timescale of the ejecta from the type 2 supernova as effectively instantaneous, and the type 1A supernova with typical timescales of 100 mega years differently. It also allows us to track oxygen and iron separately. And the good news is that when we do this, we are still able to reproduce the luminosity functions and the luminosity-metallicity relation that we were able to with the instant metal recycling in the work with Saatchi and with Nuisha. And just sort of as a quick reminder, when you look at alpha over iron versus iron, as you go down the relation, you have more type 1A supernovae, which means you have more extended star formation. So if you're looking, so as something moves to the lower right sort of part of this plot, it has undergone a much longer burst of star formation. If you were looking at a system that only underwent sort of very short bursts of star formation, you would expect it to be in the upper left, since there just weren't enough 1A supernova to put significant amounts of iron into the ISM before additional stars formed. And the thing is, there are two potential delay time distribution functions. So why does this matter? One of these is the power law from Frindelich et al. 2012. Based on star formation history, cosmological star formation histories, and type 1A supernova rates, Strolger et al. In 2020 suggested that the delay time distribution of the type 1As may actually be exponential, which you still end up at the end, sort of on billion-year timescales, you still end up with about the same number of type 1As, but they go off a little bit later than they do with a power law. For both the exponential, which you see in brown, and the exponential, which you see in pink, and the power law, which you see in brown, for the iron versus stellar mass relation, the black here are the Milky Way dwarves, and then what you see behind that are the Galacticus models for these two different delay time distributions. And we find that we're able to reproduce the luminosity metallicity relation in iron for the dwarves for both of them. But when we look at the alpha over iron versus iron relation, that's where they're different. The additional delay, that longer typical timescale before the type 1As go off for the exponential delay time distribution, means that the relation between alpha over iron and iron is a little steeper. And so the brown is the exponential. You can see that's relatively flat. You still have that declining slope that we expect to see, but for the exponential, we have a much steeper relation. The black that you see on here is the data for the Milky Way dwarfs. So this suggests that there is a clear preference within the Milky Way dwarfs for an exponential delay time distribution for type 1A supernova, suggesting that they're going off a little bit later than is thought with the power law. And to give you a sense, and just to answer the question that I think was about the statistics, each of these has 64 Milky Way mass halos run, to give you a sense of sort of the scatter.
My question was not about the statistics. So the data for the actual data, are those individual star metallicities or global?
In this case, they are individual stars. So those are the tracks for the stars, the fitted tracks for the stars for 5 of the Milky Way dwarfs. The Galacticus data, by the nature of the SAM, is the global data. I have been digging through the literature for a while, trying to find actually global alpha over iron abundances. And for the most part, it's sort of these tracks. It'll be sort of the track for the entire galaxy. There were a few, I think, in Andromeda that had it.
There is an ambiguity when you start looking at global abundances with the star formation histories, right?
Yeah,
there's a convolution of this with the star formation history. But sorry, just please go on. Sorry,
yeah, no, we're aware of that, and that's actually that's sort of the next step in doing this. So speaking of star formation histories, up until this point, I've been primarily talking about what's going on at z=0. And we also are amazingly able to replicate the star formation histories of the Milky Way dwarfs. To the right, you see the cumulative star formation history versus look-back time. The faint lines are thin lines are the Milky Way satellites, and the thicker lines are the star formation histories from Wise et al. 2014. On the left is those same star formation histories parameterized using tau 90 and tau 50. Tau 90 is the look-back time at which 90% of the stars had formed. And tau 50 is the look-back time at which 50% of the stars had formed. And sort of I've sketched up here. And this allows us to basically parameterize the star formation. So when we compared our M-body run with the Milky Way to the observations from Wise et al., we found that in general, it agreed. So if you were to look at the 3 of these, you would not see the models is looking to potentially different. We did run KS tests on the data and found that the Milky Way M31 and the M-body were all, and the modeled M from the M-body were all inconsistent with being drawn from the same distribution. And we also, but in general, we're not far off. We're able to reasonably replicate the star formation histories of a typical Milky Way or M31 mass halo. Which brings me to the main the main thing that I advertised in the abstract, which is what happens when you don't have one M-body mass halo? What happens when you run 64 1 × 10⁻¹² solar mass halos? So this is 64 extended pressure trees. It's not at 10⁻12 solar masses. So all these are the star formation histories of the dwarf satellites for all 64 of those halos. And all of the halos are chosen to be exactly the same mass. And there you can begin to see sort of some trends that the majority of the star formation histories rise very, very quickly. That is what we would expect. The majority of the galaxies are these fossils. They are forming stars very quickly and then being shut off by reionization or by early infall. You see a potential slightly higher density running along relatively constant star formation in the cumulative plot. Beyond that, and then this is the tau 50 and the tau 90 again for all 64 of the galaxies. The box that I show is that same box that was highlighted in the Weiss et al. 2019 plot where the Milky Way has no dwarves. To the left, we're colored by the stellar mass. So pink is the faintest, yellow is the brightest. And as expected, the brightest dwarf satellites are those that are continually forming stars for the longest periods of time. And the faintest satellites are the ones that are shut off much earlier. To the right, I've actually color-coded this by the z=0 star formation rate. So red is no star formation rate at all, and blue is that there is an active star formation rate. And what was interesting, and to some extent, the broad trend of this is about what you would expect. The dwarves that are the brightest, that have continued to form stars, that are in the upper right portion of this plot with are still star forming. They are blue. These are the analogs to the LMC, to the SMC today. And in general, as you move to things that had the majority of their star formation happen at earlier and earlier times, they are in general red. They're not continuing to form stars. But when you look at this in a little more detail, you see that we do actually have some galaxies that are forming stars in regions of this that we wouldn't expect. So if you note down, you can see the blue points, and I apologize, my cursor is not working. But in the lower left region of the plot, you can see that we do have some star formation dwarfs in this region that you would nominally consider to be the fossils. You would expect these to be red and dead. And I don't have the time to sort of go into this now, but if you actually look at tau 95, so the point at which 95% of the stars formed instead of 90% of the stars, many of those galaxies actually move up into the plot, and some of them they're going to look generally like Leo T. So these are objects that form stars, were quenched by reionization, and then at later times were able to accrete some additional gas and form some additional stars. But as a reminder, the local volume is not just 10⁻12 solar mass halos. We have a whole range of masses, and that's just within this inner 5 megaparsecs. As we push further out, we're going to see a larger and larger range of mass. So how does this look when you look at different masses? This is a 10⁻12 and 3 × 10⁻12 solar mass halo. It's this exact same plot. You can see, and the thing that I really want to highlight here is that when you look at the star formation histories of these galaxies, they look remarkably similar. If you sort of cover up on your screen the masses, that these are different masses by a factor of 3, you wouldn't necessarily know that they were different. The same thing's true when you look at the parameterized star formation histories in Tau 90 and Tau 50. One thing that I particularly want to point out to you is that while the brighter dwarfs that have a more extended star formation do show some scatter between them, for all of these galaxies, the low mass small dwarfs that quench early look basically the same. And these are the fossils of the first galaxies. These are these objects which are quenched by reionization, and they basically end up as tiny puffballs. This is Coma Barantises. This is the DES dwarfs. And all of those, and those exist across all of these masses. So this is 10 to the 12, 3 times 10 to the 12, and 8 times 10 to the 12. And this is the same thing. Now we're color coding it, but once again by star formation history. And what you're seeing the same broad trends across all of the galaxies. The dwarves which form over longer periods of time tend to still be star forming. In general, the dwarves which were quenched earlier tend to be red and dead. But in all of these systems, you see a few of these sort of lower luminosity dwarves, which are still forming stars. And so these are basically these Leo T analogs that you would expect to see around halos. And the exact details and the differences between these is actually something that I wanted to put out to the community. Of the question is, how do we talk about quantifying this kind of scatter? Because clearly, while the mass of the halo matters, the merger histories of the halos matter more. And the question is, how do we quantify that? So take-home points, near-field cosmology and galactic paleontology provide a critical link between the increasingly well-studied systems of the local volume and the first stars and galaxies. We can now use semi-analytic modeling to reproduce the properties of star formation histories of dwarves down to the ultra-faints on a laptop. And basically, Galacticus is a completely public code. You can download it. If you're running a Linux system, there are pre-compiled binaries. And it's an incredibly powerful and absolutely phenomenal code. The alpha abundances of the Milky Way satellites are in strong agreement with an exponential delay time distribution for type 1a supernova, suggesting that they typically go off a little later than we sort of had expected. And there is significant scatter in the number and properties of star formation histories of dwarf galaxies in host halos of the same mass. And I really want to sort of almost put forward as a challenge to the community that it's really important to figure out how are we going to quantify and talk about this scatter in order to take advantage of the absolutely unprecedented and spectacular data sets that are going to be coming down from Roman and the Habitable Worlds Observatory. And because I got to talk about the fossils, I get to use this question slide.
Very nice. Okay, I'm opening it up to the room. Who has questions? Any hands? Or just jump in. I have questions. I always have questions, but I want the room first. Ryan.
Hello. Yeah, thanks for the really nice talk. Very interesting. Regarding the type 1a delay distributions, in principle, the type 1a timings also has a metallicity dependence because that will change the binary parameters, which will change the time delay distribution from a certain star formation event. So I was curious if you're looking to try to tie that in. I think right now it seems like you're just using a single delay distribution across the entire metallicity history of your galaxies.
Yeah, we are, because this, to my knowledge, had not been done, so that we figured we'd start simple.
Sure.
The next thing we actually want to look at is, and this actually requires significant modification of Galacticus, is to actually look at the actual rates of the type 1As versus the core collapse supernova for these two models. And then that would be another thing to do, to actually put a metallicity dependence into the delay time distribution. But that is That is my running joke because I need 3 postdocs, 6 grad students, and an army of undergrads. So that's a fantastic point, and it is something we should look at, but I'm not going to make promises that's going to be done anytime in the next.
Fair enough. Thanks.
All right. Other questions? There's one. Jason. Jason, can you unmute or? Oh, I'm not hearing you. Mute, unmute.
This is the post-COVID version of Can You Hear Me Now?
Yeah. You can type it into the, and I'll ask it for you.
I can also see the chat now when I pull myself out of, I don't know why, but when I'm in slideshow mode, I can't.
Yeah, that all disappears. So.
Yeah.
So I have a question regarding the metallicities as well. Here we go. How to parameterize merger history, the number of mergers, the mass of the merging components. That is another.
Timing of most recent major mergers, but then there's the question of what do you define as a major merger? Time scale at which a given various fractions of the z equals 0 mass, dark matter mass had been accreted. So for instance, when do you build up 90% of it? When do you build up 50% of it? There has sort of been some work and sort of some thoughts on this of sort of how do you, but those are just like off the top of my head, some ideas. And then also to look at, to sort of inform that from the baryonic physics, what seem to be the primary drivers of it. When you actually look at the merger history of the host halo, if you look at things, for instance, that look more like the Milky Way satellite distribution, what do those merger histories actually look in a certain way? Are they quiescent, which you would naively expect that potentially the tau 50, tau 90 that looks like the Milky Way is going to form in a galaxy that has a relatively quiescent merger history over the last 10 billion years, but that's not something I've had a chance to look at yet. And so it may be that there's absolutely no correlation. I know when Sachi looked at this for Centaurus A, we were expecting to see a correlation with something we actually didn't, which was, so I actually don't know the answer to that, but yeah, basically when was the last major merger? When did a certain fraction of like a mass build up? Or sort of some ideas.
I have a question, but only if nobody else has one. Going once. There you go. I just have to threaten to give a question. Yes.
You have to threaten to ask a question.
Ask them. Can I unmute people? I cannot unmute people. Okay.
Hello.
Hi.
Hear me? Yeah, this is Typhon in Italy. Yeah. How do you consider the hot gas and ramp pressure process in your modeling of the SAM? Yeah.
There's a huge, for one thing, I am going to refer you to Sachi's first paper, the Weosuri et al. 2023. We have a pretty detailed discussion in that. There is a hot gas component that's in there. So it's done basically with an analytical expression. There is an efficiency for the ram pressure stripping. We found that the luminosity function of the Milky Way satellites was best fit by a relatively low efficiency for the ram pressure stripping. So you basically say you come in, there's an efficiency set. The exact equations I do not have in front of me right now.
See, okay. And the second one is the second small question is here. For my understanding, here your paleontology is the same as archaeology, right?
Is what?
The paleontology is the same as well as the archaeology, because we normally we will call the galactic archaeology. Here, yeah, you call the galactic paleontology. So I'm a bit
there's a subtle difference to this, and that is here, and I perhaps should have spent a bit more time on this. I think of galactic archaeology as using stellar streams and dwarf using stellar streams and the dwarf galaxy population to try to reconstruct the merger history of a galaxy. It's done primarily for the Milky Way using 7D phase space with positions, velocities, and metallicities. And to me, that's galactic archaeology. The difference to me for galactic paleontology is the idea that what we're doing is we're looking at these incredibly faint dwarf galaxies. And I mean, these are the ultra faints. These are galaxies that if you literally looked at them next to a star field, you would not be able to tell which one had a galaxy unless you'd colored the stars in. So these are incredibly faint galaxies. Their progenitors were so low mass that they were below something called the filtering scale. So the filtering scale is set by the temperature of the intergalactic medium. So everything forms bursty stars before reionization, is undergoing sort of these bursty modes of star formation. When reionization reheats the intergalactic medium, it sets a filtering scale, and that is somewhere between 20 and 30 kilometers per second for Vmax. If a halo remains below that, effectively its star formation is frozen out. So it will form a few more stars after reionization, but effectively it's quenched by reionization. Because of that, its stars are frozen out 12 billion years ago. And so we can actually directly relate sort of that fossil galaxy and the properties of those fossil galaxies to what was going on during the first billion years. And it's exactly the same way that we know what a triceratops looks like, based on sort of the fossils that the dinosaurs left behind. We haven't gone back to the Jurassic. Unfortunately, that we don't have a telescope that can do that. So that to me is the difference.
Okay.
They're very much related and they're interconnected, but to me that's sort of what galactic paleontology is. You're really looking at those really, really tiny galaxies that were frozen out by reionization. And like I said, it's a really good excuse to use dinosaur bones in my talks.
Okay, thank you.
Okay, I'm going to ask my question now. So this is about the Milky Way. So the type supernova 1A delay times, it's a little up with
This one?
Yeah, exactly. So the black lines are from
From Kirby et al. I want to say 2014. And they are fits to the alpha over iron versus iron abundance for the stars in 5 of the ultra faints.
So this is isochrones, right? So
Yeah, these are the fitted isochrones. For Galacticus, we only have the global properties. And if anyone knows where I can get global alpha over iron abundances for the Milky Way and Andromeda dwarfs, please tell me, because I've spent a huge amount of time digging through the literature, and I think I found 5 Andromeda dwarfs that actually had global values, and they all sit down here. So they actually are also in agreement with the exponential delay time distribution.
Right. I think you're going to get statistical samples with UVEX because it's going to do ultraviolet spectroscopy of, aperture spectroscopy of all these little dwarf faint UV sources. So there are going to be star forming. No fossils in there, I think. I mean, they won't target fossils, but there is going to be a lot of spectroscopy for the whole galaxy on the faint end. And so you might be able to get to populate this further.
It would be nice. We're trying to actually get this out a little sooner than that.
Yeah, no, fair.
Partially because to me it's a really interesting result, and I'd like to get it out to the field as quickly as I possibly can. But no, do you know when those observations are going to be done and come down the pipe?
I mean, first the thing has to launch, but it is.
Well, there's that.
It's the other UV mission, and I think that might give you some extra points here as well. But on the star forming part side, the isochrones are really. I don't think Euclid isochrones would help you much. Some Euclid expert will have to jump in here, but I don't think that's only near infrared, so I don't think that has enough discriminatory power to tell you between the two, to alpha over. So yeah, I think you might be stuck with these lines just for now.
Yeah, that's one of it was driving me nuts. I was just like, okay, can somebody just do an average, give me, the same way we have, the average iron metallicities for the dwarves. Can I get an average alpha over iron? And it, near as I can tell, it didn't exist. And by the way, I'd like to apologize if you heard my cat in the background. I swear she has been fed. She is a very happy fluff ball, but mommy is not paying enough attention to her currently.
I mean, they can see the bottom of the ball, right? So, okay. Any other questions? This is really exciting. I think it's really neat that we can see the delay time of supernova. That's a new one. That's
The clarity of this, the clarity of this blew us away.
Yeah.
Like the clarity of between the two was sort of what surprised me. And I agree, we need to come up with a way to parameterize the merger histories and think about how we parameterize the merger histories. And that's something that I don't know that we have a clear answer to yet. But it would be nice if we had one before, we got these data sets.
I had a question about the slide that you just showed with the
This
three
one?
the three halos with
This.
yes.
Yeah.
So not only do you get so the red and dead always seem the same, like they're all stuck in the bottom corner there, but you have ones that are still star forming, and the bigger halo, the less you have. I think that's a known result, but I noticed that they all still have a Magellanic cloudish kind of thing. Is that right? Or
Yeah, they all still have some sort of star forming. They all still have something, but what fraction of the halos would have that, I haven't sort of run yet.
because that was like how typical is our local group, or at least our Milky Way Andromeda grouping, is still an outstanding question. And what it looks like from here is like, well, no, an LMC is not that weird to have floating around. Is that about
Yeah,
right?
it's not. I think what's weird is having both.
An SMC and an LMC.
And an LMC. It's having the pair that's particularly strange. But one of the things that and I could not get, I was working last night to try to get the KS test working, but one of the sort of the next step that I want to do is to actually run a test to determine, can you draw the Milky Way and the Andromeda tau 50 and tau 90 data from these distributions?
Okay.
So are they, my kind of intuition is the answer is going to be yes. That if you've run enough halos, if you build a large enough statistical sample of, 10 to the 12, 2 times 10 to the 12 solar mass halos, that you can draw both of those distributions from those halos. It's equivalent that you can sort of draw the observed distribution from those halos. And then the question becomes, is there a difference in the merger history that produces those two distributions that look like those galaxies?
Nice.
But yeah, there are sort of these subtle differences, like you pointed out with the star forming galaxies, but in general, they looked remarkably similar for halos that are nearly an order of magnitude apart.
Yeah, as soon as you got big, you got big. That's okay.
Yeah, pretty much once you get to a certain point, you're there.
Yeah. All right. Fantastic. Okay, we're coming up on the hour. Is there any last minute question that we want to ask Mia? And otherwise, I am going to thank our speaker very much for our talk. Thank you so much all for coming. Will be a talk in October. Clappy.
Feel free if you've got questions, or ideas of things to do with this data set, please send me an email.
Okay. Thank you all so much, and I'll see you next time. Thank you,
And
Mia.
John, and hi, John.